Hello and welcome in today's video. In today's video, we are going to look at the cofactor expansion. That is a method that is used to compute the determinant of any n by n matrix and also the computation of the inverse of any matrix of any order or any square matrix of any order. So in this case, we are told to consider the matrix A with the entries A11 all the way to A33. So in this case, for each entry Aij in your chosen matrix or chosen row or column, there exists this value that we are calling Mij, which is equal to the determinant of the remaining n minus 1 by n minus 1 matrix, which is obtained after deleting the ith row and the ith column. So in this case, when we talk of this Aij, this first I tells us the position of that entry row wise, and this entry tells us the position of that entry column wise. So that's in this case we have in that this A11 means that there's an entry that is in row 1 and the column 1. When we talk of A12, is an entry that is in row 1, column 2. When we talk of A32, is an entry that is in row 3, but column is 2. So we talk of, in general, just Aij, where I is the position of that entry row wise, and J is the position of that entry column wise. So in this case, we are just choosing a 3 by 3 case. So how do we compute this Mij? So for example, you can talk of Mij where I is equals to 1 and J is equals to 1. So for this case, we shall have M11, which would be equal to the determinant. By determinant, we mean this, the determinant of the matrix that is obtained after we delete this row and this column of that particular matrix. In this case, we'll be left with the determinant of A22, A3, or A23, A32, A33. So for example, if we have an AB23, this will be equal to, so for this case we delete the second row, which is this one, and the third column, which is this one. And this is just ignore the other colors because that is already reinstated. So in this case, we'll be left with the submatrix with the entries A11, A12, A31, A32. So should you find this determinant and this determinant, already this is going to give us what? A22, A33 minus A32, A23 is going to give us what? So these are 2 by 2, you multiply this times this minus this times this, it is going to give us A11, A32 minus A31, A12. Now this means that each and every entry here has a corresponding minor. So when you talk of A11, that is A small 11, then you should think of the minor M11. When you talk of A12, then you should think of the minor M12. When you talk of A13, we should think of the minor M13, and so on all the way to A33, which should give us what? Our M33. So meaning that it is a minor corresponding to this entry, this to this, this to this, and all the way to the last one. And the minor is just a determinant like we've shown in this particular case here. You just singled out 2 cases, that is M11 and M23. So next we define what we call a cofactor. We've seen already that each and every entry in this particular matrix has a corresponding minor. So as well, it should have a corresponding cofactor. And the cofactor, which is denoted by Cij, it is given by -1 raised to the power of I plus j multiplied by the corresponding minor. So for example, if we have this entry A11, like in our matrix here, then they should give us the cofactor, which we should denote by C11. If we have an entry A12, then they should give us a cofactor that we should denote by C12. And this would be given by, for example, if it is C11, this would be just -1 raised to the power of 1 plus 1, then multiplied by M11. This would be equal to -1 raised to the power of 1 plus 2 multiplied by M12. And this goes all the way to A33, which would give us what? C33, which would be equal to -1 raised to the power of 3 plus 3 multiplied by M33. So whereby M1, M12, all the way to this one, the minors corresponding to these entries in our matrix. That is these ones all the way to the last one. But something is going to happen here. What does this -1 raised to the power of I plus j? Or what impact does it have to this minor? So I want you to look at this. So in this particular case, we have that we are given an entry A11, then the corresponding cofactor, it will be C11, which will be equal to -1 raised to the power of 1 plus 1 multiplied by M11. And in general, we said that Aij, where this I is the position of that entry column wise or row wise, this j is the position of that entry column wise. It should give us what? A cofactor that we are calling Cij, which will be equal to -1 raised to the power of I plus j multiplied by Mj. So there are two cases there are two things that are going to happen in. That is -1 raised to the power of I plus j. So this I plus j could be an even number, but this I plus j could be an odd number. So should you raise -1 to an even number, the outcome will be +1. And should you raise the -1 to an odd number, the outcome should be negative. So the only thing this I is doing, or -1 raised to the power of I is bringing on board, -1 raised to the power of I plus j is bringing on board, it is either +1 or -1. That is, it is either multiplying the corresponding minor by -1 or +1. So we can conclude that a minor or a cofactor, it is just a signed minor. So now, for you to be able to compute the determinant of A using the cofactor expansion, what you need is pick the entries A11. This is your O1, this is your O2, this is your O3, this is your column 1, column 2, column 3. So determinant is given by any row or column. You multiply by their corresponding cofactors and you do the sum of the products. For example, if we take row 1, we can multiply A11 by C11 plus A12 multiplied by C12 plus A13 multiplied by C13. That is row 1. You can also compute it along row 2. This will be A21 you multiply by C21 plus A22 you multiply by C22 plus A23 multiplied by C23. And these will add or even any column. For example, if we pick column 3, then the determinant of A will be equal to, you pick the entries in column 3, that is A13 multiplied by the corresponding cofactor, which is C13, plus A22 2, 3, you multiply by C2, 3, plus A3, 3, multiplied by C3, 3. All these will give you the same determinant, meaning that you can compute the determinant of the matrix A along any row or column. All of them will give you the same determinant. So we look at an example on how to compute the determinant of a 3 by 3 matrix using the cofactor expansion. So for this case, you are told to compute the determinant of A, which is having these entries, by cofactor expansion. So for this case, I have chosen row 1. So we are going to compute this particular determinant along row 1. So we have the entry number 1, 2, 3. That is, in row 1 we have 3 entries, that is 1, 2, and 3. So this entry has a corresponding cofactor. This entry has a corresponding cofactor. This entry has a corresponding cofactor. So we just need to compute their cofactors, multiply by these entries, then you do the sum of the products. So we need our C11, and C11, it is the entry that it is a cofactor that is corresponding to this entry, which is number 1 there. And this will be given by, from the formula for the cofactor, it is negative 1 raised to the power of 1 plus 1. The reason as why we are saying 1 plus 1 is because 1 is in row 1 and column 1. Then you multiply by the determinant of the matrix that we obtain once we delete this row and this column. You realize that we'll be left with this submatrix here, which is having the entries 5, 6, 8, 9. Remember we said that determinant is what we are calling the minor. Then plus, if we multiply by this, you get the cofactor. So C11 will be equal to this value here. We all know that this times this minus this times this is going to give us negative 3. But however, should you raise negative 1 to 2, because we know that 1 plus 1 is equal to 2, the answer will be positive 1. And now positive 1 times negative 3, that will give us negative 3. Next, it is C12. That is the cofactor corresponding to the second entry. This entry is in row 1, but column is 2. So C12 will be equal to negative 1 raised to the power of 1 plus 2 multiplied by. So why 1 plus 2? This is the position of that entry row wise, position of that entry column wise. So this is row 1, the column is 2. You multiply by the determinant that you obtain once we delete the first row and the second column. And you'll be left with this matrix here, which is having the entries 4, 6, 7, 9. So should you compute this, know that this times this minus this times this, it is going to give us negative 6. But however, this negative 6, it is multiplied by this negative here. Why negative? Because this is negative 1 raised to the power of 1 plus 2, which is 3. Now we said that should you raise negative 1 to a power which is odd, the answer is always negative. So negative 1 times negative 6, that's why we are saying that we are getting positive 6 here. The third one, which is the cofactor 1, 2, 1, 3, which is corresponding to this entry 3 here. It is equals negative 1 raised to the power of 1 plus 3. Because you know that 3 is in row 1, but column is what? 3. So 1 plus 1, you get 4. So negative 1 raised to the power of 4, we get positive 1. But again, we are multiplying this by the minor. And the minor, it means that we delete this row and this column. So once we delete that row and this column, we'll be left with this submatrix, the entries 4, 5, 7, 8. And now computing this determinant, this would be 4 times 8 minus 7 times 5, which is going to give us negative 3. And of course, negative 3 multiplied by positive 1 that we are getting from this part, we get negative 3. So therefore, the determinant of A will be given by A11 multiplied by C11, A12 multiplied by C12, A13 multiplied by C13. Then you do the sum. Suppose you know what is your A11, A12, A13. These are the entries in the first row. So and you should do that because already you've computed the C11, C12 and C13. So you just need to replace them here in this particular expression or formula there. And these will be the same as what? You take 1, you multiply by -3 plus 2, which is here, you multiply by 6 plus 3 multiplied by -3. Now should you simplify this? This will be -3 plus 12 minus 9, which is giving us 0. That is, we have computed that determinant along row 1. You can also compute the determinant along, maybe let's pick column 3 in this case. I want to justify that. Should you compute the determinant along any row or column, you should always get the same determinant. So we can also compute this determinant along column 3. Because we said that should you compute the determinant along any row or column, then it should be the same. So I picked column number 3. So what are the entries in column number 3? It is 3, 6, 9. So the cofactor corresponding to 3 will be denoted by C13, meaning that our C13 will be equal to -1 raised to the power of 1 plus 3 multiplied by the determinant of the submatrix that we obtained once we delete this row and this column, and be left with the entries 4, 5, 7, 8. Should you compute this will be the same as what? This times this minus this times this, you get -3. So -3 times this will be positive because the power here will be even. Because 1 plus 3 you get 4. So meaning that the negative remains. So next is the cofactor corresponding to 6. 6 is in row 3, row 2, column 3. And we are denoting that by C23. So C23 will be given by -1 raised to the power of 2 plus 3. 2 plus 3 because 6 is in row 2, column 3. Then you multiply by the determinant of the submatrix that you obtain after deleting this row and this column. And these will be having the entries 1, 2, 7, 8. That's why we are saying that should you multiply this times this minus this times this, it is supposed to give us -6. But -6 will be affected by this -1 raised to the power of 2 plus 3. Because you know that 2 plus 3 is equals to 5. So -1 raised to the power of 5, you get -1. So -1 times -6, you get +6. Next, it is the cofactor corresponding to 9. 9 is in row 3, but column is 3. So meaning that the cofactor, which is denoted by C33, will be equal to -1 raised to the power of 3 plus 3 multiplied by, in this case you are going to delete this row and this column, and you will be left with a matrix 1, 2, 4, 5, which is equals to, so in this case it is 1 times 5 multiplied by 4 times 2, which is going to give us -3. But -3 multiplied by this, it will be just -3, because this is -1 raised to the power of 6, which is an even number. So -1 raised to an even number, we say that it is +1. So +1 times -3, you get -3. So therefore, the determinant of A along row or column 3, it will be equal to A13 multiplied by, from the formula, A13 multiplied by C13 plus A23 multiplied by C23 plus A33 multiplied by C33. So already you have these values and also the cofactor, the corresponding cofactors. So meaning that this will be the same as what? 3, which is here, multiplied by -3, which is the corresponding cofactor, plus 6 multiplied by +6, which is the corresponding cofactor, multiplied by 9 or plus 9 multiplied by -3, which is the corresponding cofactor. Now should you something, this will be -9, this will be plus 36 minus 27, which is giving us a 0. You can see row 1 and column 1, they are giving us the same determinant. So this is to justify that should you compute the determinant along any row or column, you should get the same determinant. So in summary, we are saying that for you to be able to compute the determinant of any matrix, you just need to pick any row or column that you want to compute the determinant along, then find if it is the ith row, you find the cofactors corresponding to the entries in the ith row. So multiply each entry in that particular row by the corresponding cofactor, then sum those products. So this will automatically give you the determinant of that particular matrix. Thank you for watching.